Okay, welcome back, and today we are going to continue on with Chapter 11 and with the chi-squared distribution. And today we're going to start one of the three tests. And the test that we're going to talk about today is the goodness of fit test. And the goodness of fit test is a chi-squared test for seeing whether a sample distribution fits a particular, sample distribution fits a particular claimed distribution. Okay, so it could be any distribution. It could be uniform, it could be normal, binomial, exponential. We can test for any distribution, given the, as long as we know the formulas and things like that. Or we could be given a specific distribution. So the chi-squared distribution, the chi-squared goodness of fit test, tests whether a data set or whether a given sampling distribution fits a particular distribution or not. Okay, and so now here's the hypotheses. Okay, so these are the two hypotheses that we're going to have. So the null hypothesis is always going to be that the data fits the claimed distribution. Versus that the data doesn't fit. Okay, and so remember, we're always going to assume the null is true, and then if there's enough evidence against that, then it would support that it does not fit that claimed distribution. Okay, so here's the test statistic that we have to calculate. Okay. So it's a chi-squared test statistic, of course, and the formula is this. That's the formula. Oh, sorry, missing one piece. There we go. So it's the sum of all of these for each category. Okay, so again, there's different categories that we're going to look at, because if we look at a frequency distribution, we've seen that it's for different categories of a random variable. Okay, so in this case, we're going to take the observed value. So that's what O stands for. That's the observed value that we're given. That comes from the data. Minus the expected value. Well, what's the expected value? The expected value is the value of the frequency that you would expect to fall into that category if the null was true, if the data did fit the claimed distribution. Okay, and so we'll talk about that in a moment too. But realize that this is the observed value minus the expected value, that quantity squared divided by the expected value. And we're going to take those calculations for each category and then sum them up over all categories. So I'm going to put for k equals 1 to I. Okay, so this k represents the number of the categories. Okay, or actually no. How do I want to do this? No, I don't want to do that. No, I don't want to use n either. Never mind. Anyway, so in this case here, the degrees of freedom is equal to the number of categories minus 1. So in the chi-squared tests for the goodness of fit test, realize that it's the degrees of freedom, which we normally would think is n minus 1, is not n minus 1 in this case. It's the number of categories minus 1, or what we denote as k. So k minus 1, where k is the number of categories or groups, not groups, the number of outcomes, you could say. Okay, so it's going to be the number of categories minus 1 is degrees of freedom. And so that's what we're going to use to test the hypotheses. Okay, so now, here are the assumptions. Actually, before we get into that, one thing to realize that this test is always a right-tailed test. Okay, and the reason why it's a right-tailed test is because, think about it this way. The idea here is if the data does fit, let's assume that the data does fit the distribution. Then if the data does fit, then we would expect, we would have our observed values pretty close to the expected values, right? If the data fits the distribution, that if we calculated what we would expect, those values should be pretty close to each other, right? Which means this difference should be pretty small. And so if that's the case, then if we calculate this test statistic, it should be pretty small. On the other hand, if it doesn't fit the data, if our data doesn't fit the distribution, then the expected value shouldn't be close to the observed value, and so these differences should be large, and then of course this whole thing should be large. So in other words, if this thing is too big, that's going to be evidence against the null and support the alternative. Okay, so that's why it's a right-tailed test. We're going to reject the null if our test statistic is too big. Okay, so this is a right-tailed test. Okay, now here are the assumptions that we need to, or the conditions that need to be met, the assumptions and conditions. Okay, so of course the assumptions is that we're having a random sample. So of course we're dealing with random samples. Let's see here, anything. Yeah, random samples. And the other thing too is the condition is that for each category, okay, for each category, the expected value for each frequency in each category needs to be bigger than or equal to 1. So the expected frequency for each category under the null needs to be greater than or equal to 5. Okay, so this needs to be met. If it's not met, then that's going to cause problems with this test. Okay, so we can't do this test if any of the categories has an expected frequency of less than 5. Okay, so here's the way we would set up our hypotheses. So let's do an example. So this is the way we're going to set the hypotheses up. So in reality, when we do this, it's going to be, we're going to say that P1 is equal to some percentage, and then P2 is equal to some percentage, all the way down to P sub k for however many categories we have. Okay, so this would be the null hypothesis. We're saying, okay, the proportion of data that falls into this category we believe is this percentage. The proportion of values or frequency that falls into category 2 is this, all the way to the kth category. And so that's going to be our null hypothesis versus H sub A, which is at least one P is different. Okay, so that's what we're dealing with. So now let's do an example. And let me see here. Let's do one that deals with uniform. Okay? So let's do an example that deals with a uniform distribution. Okay? So remember, with the uniform distribution, the key is that the outcomes are equally likely. Okay? So let's use that. Okay, so here's an example. And it says here, employees want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent uniformly during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as in the table below. For the population of employees, do the days of the highest numbers of absences occur with equal frequency during a 5-day work week? Test with a 5% level of significance. Okay, so in this case, the sample size is 60, and we're gonna write down the data, the observed values, in a moment. But first, let's set up our hypotheses. So, the claim is we're testing, does absences occur uniformly across the weekday? So are absences uniformly distributed over the 5-day work week? Okay, so now our null and alternative hypotheses then are going to be as follows. Now, we're going to assume that the data fits the distribution. So in this case, we're going to assume that the data fits a uniform distribution. So what does that mean? How do we write that? Well, how many days do we have? We have 5 days, okay? And if we assumed that absences were uniform across the 5-day work week, and we have 5 days, then what percentage of the absences would we think would fall into each day? Well, if it's equally likely, well, how many days do we have? We have 5. And if it's equally likely that absences should occur with equal probability or equally likely, then we would expect that 1/5 of the absences should fall on each day. So the way we would write the null hypothesis in this case is that P1 for the first day, right, is equal to P2, which is equal to P3, which is equal to P4, which is equal to P5, and of course all of these should be equal to what? 1/5, okay? Or 20%, right? So you could also write 20%. Okay, we're going to use 1/5 in a minute, but basically you're saying the proportion of absences on each day of the week should be 20%, okay? Versus the alternative, which is at least one P is not 1/5, right? So that makes sense. So that's step one, and of course the claim, right, is the null, right? We want to test the claim that it's uniformly distributed. Okay, so now, step two. We're going to assume the null, right? Always assume the null is true. And then step three, of course, is we're going to write down the information, starting with their alpha level. And in this case, they want us to use an alpha level of 0.05. Now, here's where we're going to write down the observed value. So here's where the table comes in, okay? So I'm going to write down the table. So here's the day, right, or category, right? So we got 5 days. You'll see in a minute why I'm doing this. Okay, so here's the day 1, 2, 3, 4, and 5. Okay, so Monday through Friday, right? And if you want to use M, all the initials for the days of the week, that doesn't matter. Okay, so the first thing is how many categories do we have? Well, we have 5 days, so that's 5 categories. So what's the degrees of freedom? Well, the degrees of freedom then is equal to k minus 1. In this case, number of categories is 5. So the degrees of freedom is going to be 4, not 55. N, or 59. N is equal to 60. That's the sample size, right? The degrees of freedom is not 59 or 59. Okay? So just be aware of that. So N is 60, alpha is 0.05, and the degrees of freedom is 4. And so now I'm going to write down the observed values. The observed values is what's in the table. And so I'm going to write down what's in the table. So on Monday, there's 15. Tuesday, 12 absences. Wednesday is 9. Thursday is 9. And Friday, 15. Okay? So look at that. It's kind of strange. Friday and Monday both hit the highest. Anyway, so now the expected values, the expected frequencies. Okay, how do we figure out the expected frequencies? Well, the expected frequencies is based on the assumption that the null is true. So if the null is true, we would expect that the frequencies each should be 20% of what? 20% of the 60. So we would expect, if the absences are uniform, that 1/5 of 60 should be in each one of these. And so if we take 1/5 of 60, right, so if we take, so our P, right, is going to be 20%, right, of 60, or 1/5 of 60, and we're going to get 12. So all of these expected values, we would expect to be 12. Okay? And so now all of these, and of course, just so you know, so P is equal to what? It's going to be, or P hat rather, if you want to, no, let's not state. It's going to be P sub I, let's do that, for each one of these. And what are we doing? Well, we're going to take 1/5 of the 60, and that's where we get 12. So each one of these should be 12. Now, there's our observed values and our expected values. Notice how all of these expected values are at least 5. So we're good. Okay, so we've got our condition met. Okay. If one of these was less than 5, we wouldn't be able to do this test. Okay. Now, here's how you have to do it on the calculator. I'm going to show you the traditional method and the p-value method, and I'm going to show you 2 different ways to do it on the calculator. The first way is if you do not have the goodness of fit test on your calculator. And some of you won't. If you have a T83, you may not have the chi-squared goodness of fit test on your calculator. So I'm going to show you how to do this on the calculator without that function, and it's not going to be that much harder to do. Okay. Now, the first thing you need to do, and this is regardless of which, if you have this chi-squared goodness of fit test on your calculator or not, what we need to do is we need to enter our observed values and our expected values into our calculator. So I'm going to put this into list 1, and I'm going to put my expected values into list 2. Okay? So go ahead and do that also. So let's see. So I'm going to put in, so stat edit. Okay, so now I've got both my lists in there. Now I need to calculate my test statistic. Now remember, the test statistic chi-squared star is this formula, the sum of O minus E squared divided by E. Okay, so now what I'm going to do is I'm going to use this formula in my calculator. And you're probably wondering, well, how am I going to do that? I'm going to take this piece here, and this is going to go in my last column, my last list, which is going to be L3. And so what I'm going to do is I'm going to use my first 2 lists to make this formula. So I'm going to do O minus E squared divided by E. And so I'm going to use L1 and L2. So what I'm going to do is I'm going to have, in column 3, I'm going to use L1 minus L2 quantity squared divided by L2. And this is how you're going to do it. Okay, so I'm going to show you. So now I'm assuming you guys have your lists already in there. Okay, so I'm going to show you. So here's my 2 lists. Okay, now I'm going to go to my list 3. See where my highlighted bar is? So now watch what I'm going to do. I'm going to highlight the top of the bar. Okay, and so I'm going to scroll up. So I'm going to scroll up. I'm going to highlight L3. Okay, see how L3 is now black or highlighted? So now what I'm going to do is notice at the bottom here it's blank. Okay, right here. So it says L3 equals. So now what I'm going to do is I'm going to type in L1 minus L2 in parentheses and then square it and then divide by L2. Okay, so now I'm going to do parenthesis. So I'm going to try to do this here. Okay, so I'm going to do, parenthesis, and then I'm going to do second 1. Okay, so I'm going to go second 1. Okay, well, let me just type it in. So I'm going to talk while I'm doing it. So I'm going to do parenthesis, L1, so you have to do second 1 to get to L1, then minus, and then second 2 for L2, and then I'm going to do parenthesis. Then I'm going to do the x squared key, and then I'm going to hit divide, and then I'm going to hit second 2 for L2 again. And so now, this is what I have. So right here, I have the formula. Okay? So now all I'm going to do is hit enter and watch what happens in this column when I hit enter. There are all of the values for the formula. Okay, so now what I just did was I calculated this formula for each of the categories. So what I have, and I'm going to write it down just so you guys see what they are. Okay. So this turned out to be 0.75, 0, 0.75, 0.75, 0.75. And so now what I'm going to do is I need to sum this column up. So now here's what you need to do. To get to the list, you need your lists menu. So what you're going to do is once you have list 3, now what you're going to do is you're going to quit out of here. So go second, quit, second mode to quit. And now what you're going to do is you're going to go to second stat. And then that's going to bring you to your lists menu. Okay, so this is going to take you to your lists menu. And then what you want to do is you want to go to math. And then from there, you're going to go to sum. And that's what you want. Okay, so you're going to go second stat. So I'm going to do that right now. So second stat. And I'm going to scroll over to math. And then number 5 is sum. Now, what you're going to end up with is this at the top of your screen. So now all I'm going to do is I'm going to put L3 in there. So I'm going to do second 3. So now I'm putting L3 in there. Now all I have to do is hit enter. And there's my sum, 3, which obviously we could have did it ourselves by adding these up, but that's the statistic. So that's my chi-squared statistic. I just calculated it, that it's 3. Okay? Now, again, it took us a few minutes to go through that, but I'm taking my time on an exam or doing the homework. This is going to become quick. Okay? All you have to do is put your observed values into list 1, your expected values in the list 2, do this formula for list 3 and then hit enter, and then just go to second stat, lists menu, math, sum, and just stick L3 into your sum function and you're done. That's gives you your test statistic. If you don't have the chi-squared goodness of fit test on your calculator, you have to do it this way. This is the easiest way to do it. Okay? So now that we got our test statistic, now we can do our comparison. So in this case, we're doing steps 3 and 4 at the same time. This is step 3. Step 4 starts right here, okay, where we're calculating our test statistic. Okay? Now, step 5 is our comparison. So step 5 well, what do you want to do? Well, we can do the chi-squared, so we're going to do the traditional method. Let's do that first. So the traditional method. And so we've got chi-squared star, right, is equal to 3. And now it's a right-tailed test, so we want to test to see whether it's bigger than or equal to our chi-squared r value. So what is our chi-squared r value? Well, remember, we need the degrees of freedom, which is 4 in this case, and we need our alpha level, which is 0.05. So if we go to the table, so again, if we go to the table, chi-squared r is going to be what? So I'm going to look for degrees of freedom 4. And it's a right-tailed test. We're on the right side of the table. And I'm looking for 0.05. So it's 9.488. So this is 9.488. So that's my chi-squared value, or critical value. Okay. So this is equal to 9.488. Okay. Do I have it on there? Yeah, barely. Okay. So here's the comparison, right? So with the traditional method, well, you know what? Let me put this over here. So this would be 4. 4 is right over here. So this would be 4. And so our chi-squared value is 3. This is 4. Now if you want to do the p-value method, okay, so here the comparison is our test statistic bigger than or equal to our critical value. In this case, it's not, right? So this is not. So in this case, our result is going to be, therefore, we fail. To reject the null. And then our conclusion is now what? If we fail to reject the null, what does that mean for our claim? It means that we do not have enough evidence to reject the claim that absences are uniformly distributed, which means we can't reject the claim that absences are uniformly distributed. Okay? So at an alpha level of 0.05, there is not enough evidence to reject the claim that absences are uniformly distributed across the 5-day work week. In other words, the data fits the claimed distribution based on the data. Okay? So now the p-value method, we still have to calculate our test statistics. So this, we still have to do this. Okay? So we can't get around to doing this when we do the p-value method. So the only thing we don't have to do is this. We don't have to look at the chi-squared. So everything else we still have to do. Okay? So now with the p-value method here, once we have this, if we want the p-value, then remember it's a right-tailed test, so it's going to be the probability of what? That our chi-squared test statistic, chi-squared star, is greater than or equal to what? 3, what we got from our calculation. And so here's where we're going to use the chi-squared CDF function on the calculator, which is similar to the TCDF, in that the first argument is going to be the lower bound. In this case, the lower bound is 3. The upper bound, because it's a right-tailed test, will be 10 to the 99th power, because it goes off to positive infinity. And the last thing is the degrees of freedom. So remember, the degrees of freedom is 4 in this case, not 59, because it's the categories minus 1. So it's going to be 4. And so if we look at the p-value now, let's go to our distribution menu. So go to second bars. And we're going to scroll down to 8. And now we're going to put in 3, comma, 10 to the 99th power, comma, 4. And we get 0.5578. 0.5578. Huge p-value. Definitely not less than alpha, right? So if we go to our comparison here, p-value is equal to 0.5578. Less than, it's definitely not less than alpha equal to 0.05. So there's our comparison. Again, we failed to reject the null, and our conclusion is still the same. Okay? So now, let me show you how to do this with the goodness of fit test function, okay? So now what I'm going to do is I'm going to erase some of this. And so I'm going to leave some of this up here. So I'm going to erase this column here because we don't need it. Okay? But we do need this. Okay? So at step 3, we still need this information here. And we still need to put our two lists together in the calculator. Okay? And we still need to check everything. Still need the degrees of freedom. But what we're going to do is in step 4, which I'm going to erase this. And so in step 4 here, now we're going to use what's called the chi-squared GOF test on your calculator. And the only thing you need to put in the calculator are 3 things. You need to put in your observed list, your expected list, and your degrees of freedom. So in the calculator, it's going to want your observed list first. So you need to put in L1. And then it's going to ask you for your expected list. That's where you're going to put in L2. And then it's going to ask you for degrees of freedom. And that's where you're going to put in 4. And what happens is, it's going to give you your chi-squared statistic and your p-value. So let's do that. So you're going to go to Stat Tests and scroll up until you see chi-squared GOF test. Hit enter. You're going to, L1 and L2 are in my observed and my expected list automatically. That's by default. So if you put your lists in other lists, you just have to change those. And so now let's go to enter. And look at that. My chi-squared statistic was 3, which is what we got. And I got the exact same p-value, 0.5578. So we got 3 and 0.5578, which is exactly what we did. So again, if you don't have this test on your calculator, that's fine. You can still do it using the calculator the way I showed you just a few moments ago. Okay. Now, once we have the p-value and the chi-squared, you could still do the same, either the traditional method or the p-value method. You get the same results. Okay. So that's that example. So now the rest of the time what I'm going to do is I'm going to use the goodness of fit test. So those of you who don't have the goodness of fit test, make sure you practice with the examples that I show how to do it. And make sure that you get the same answers that we get. Okay? So now, let's do another example. Okay, so let's see what we have. Let's do this example. One study claims that the number of televisions that American families have is as follows. 10% of families have 0 televisions, 16% have 1 television, 55% have 2 televisions, 11% have 3 televisions, and 8% have 4+ televisions. A random sample of 600 families in the far western United States resulted in the following table. And so they give us a table of frequencies, and I'll write that down in a minute. At the 1% significance level, does it appear that the distribution number of televisions of the far western United States families is different from the distribution for the American population as a whole? So in other words, our null and alternative hypotheses are going to be this. So here is going to be where we're going to write the distribution, right? That what we assume. So this is going to be the fits. Okay, so what does it fit? Well, they're saying that, so the categories are 0, right? 0 televisions, 1 television, 2 televisions, 3 televisions, or 4, well, no, yeah, or 4 or more televisions. So we've got 5 categories, right? So we can say, they're going to say that P1, right? Or no, P0, I'll call it P0. 0 televisions. The proportion of families that have 0 televisions is 10%, or 0.10. P1 is equal to 0.16. P2 is equal to 0.55. P3, well, you know what, let's just do this, I'm sorry. I just want to keep the categories because these are going to be the number of categories. So P1, P2, P3, P4 is what? That's 3 televisions, so that's going to be 0.08. And then P5, the last one, is no, this is 0.11, sorry. 0.11, and then this is 0.08. Okay, so that's the distribution. And if you add these up, you get 1, right? So you get 26, 81, 92, and 1, or 100%. Okay, so this is the claimed distribution. So this is what they want. It says, at the 1% significance levels, does it appear that the distribution, the number of televisions of the far western United States families is different from the distribution for the American population as a whole? So in other words, does the distribution for the number of televisions follow this distribution for what far western United States families? Okay, versus what? Well, the alternative is always going to be the same, that at least 1p is different, or one proportion is different. Okay, and so this is what we're claiming. This is what we're testing. Okay, and so that's step 1. And step 2, of course, is going to be, we're going to assume that it does fit. So assume the null is true. And then under that assumption, we're going to do our test. And so now here, alpha is 0.01. And now I'm going to write my table again, right? So here's, I'm going to write my table of categories. So I have 5 categories. So I have 0, 1, 2, 3, and 4 plus televisions. So again, my sample size, well actually we're going to get to that in a minute. So let me do this. So here's my expected values. Okay, so now, again, this is going to be list 1, this is going to be list 2, and so my observed values from the table that they gave me, so again, n, the sample size was 600 families, right? So again, the degrees of freedom in this case is not going to be n minus 1, it's not going to be 599. That's not, that would completely give you the wrong answer. The degrees of freedom is going to be the number of categories of televisions, or the number of categories of the number of televisions. So it's going to be these 5 categories minus 1. So the degrees of freedom, which is k minus 1, which is going to be equal to 5 minus 1, which is equal to 4. Okay? So now let's put in the value. So of the 600, we have 66 that fall into the 0 category. 119 falls into 1. 340 falls into 2. 60 falls into 3. And then 15 falls into the 4 plus category. So now here's where we have to calculate the expected values. Now, under the null hypothesis, right? That's what we're assuming. Under the null hypothesis, how many of the 600 would we expect to fall into the 0 category? Well, that's where the percentages come in. So here's the 0 category, right? So what percentage would we expect to fall into that category? 10%. So how do we get the expected value? We take 10% of the 600. So what's 10% of 600? 60. So that's going to be that value. Now the next one is 16%. So 16% of 600 we would expect to fall into that. So I'm going to take 0.16 times 600. And that's going to be 96. So this is 96. And then the next one is 0.55, right? 55%. So if we take 0.55 times 600, I get 330. And then the next one is 11%. So 11% of 600 is 66. And then the rest have to fall into here because all of these have to add up to 600, right? So now the last one is 8%. And I'm not going to add, it's easier just to multiply. And we get 48. And so you just want to check and make sure that these two columns add up to 600. Okay? If this one doesn't add up to 600, then something went wrong. Okay? And double check your calculations. So now notice these numbers. I think they're fairly close except for this one and this one. So who knows? Okay? Maybe, maybe not. Okay? So now here's what we're going to do. Now I'm going to go to step 4. And I'm going to use the chi-squared goodness of fit test. And so what I'm going to do is I'm going to enter my L1, observed values into L1. Right? My expected values into L2. And then my degrees of freedom is 4. Okay? So I'm going to do that right now. You guys do the same. So let's see here. Okay, so now I'm going to do the expected values. And I got 60. Okay, and so now all I'm going to do is I'm going to go to my goodness of fit test under stat tests. And I'm going to go up to goodness of fit test, and L1 is my observed value, L2 is my expected value, 4 is the degrees of freedom, and now my chi-squared test statistic is 29.65. And my p-value is 5.78 times 10 to the negative 6th. So in other words, 0.000006. So extremely small p-value. And so, again, step 5, I'm going to use the p-value method. So p-value is very small, so basically just about 0, which is definitely less than alpha equal to 0.01. And so, what does that mean? Well, we're going to therefore reject the null. And so, in this case, going back to the conclusion, what are we going to do? Well, at an alpha level of 0.01, there is strong evidence, in fact, I would say that there is very strong evidence to reject the claim that the distribution of the number of televisions for families in the far west United States follows the distribution for the United States as a whole. So again, based on the sample data. So again, let me repeat that. So at an alpha level of 0.01, there is very strong evidence to reject the claim that the distribution of the number of TVs that families have in the far western United States fits this distribution based on the sample data. Okay, so that is, let me see if there's anything else here. Oh, by the way, also notice that all of our expected values are greater than or equal to 5. So we're good there. Let's see here. Anything else? Yeah, that's it. Okay, so next time, guys, we're going to talk about the test for independence and talk about how that's also a chi-squared distribution. And in fact, it uses the same test statistic, but we are testing a different question, okay, a different claim. So I'll see you next time.